So this is the last part of my module 1, the part 3 of basic principles, concepts, definitions in thermodynamics. Now, the atmospheric pressure. A barometer is used to measure atmospheric pressure. Now, there are certain problems that stated that the barometric pressure reads blank pressure, or its atmospheric pressure reads blank pressure. Now, when we say barometric pressure, it is understood that it is automatically be a atmospheric pressure. Now, the formula of barometric pressure or the atmospheric pressure is atmospheric equals gamma height, where HO is the height of column of liquid supported by atmospheric pressure. Now, to further elaborate our discussion, here is problem number 1 for us to solve. Problem number 1, a vertical column of water will be supported to what height by standard atmospheric pressure? Now, as you can see here in the problem, there is no given, there is no figures. All we have is the word at standard atmospheric pressure. Now, this means that when it is on standard atmospheric pressure, it means it is on standard condition. Like for example, when we say standard condition, we have constants. We should know the constants in standard conditions. Here our mother equation, our general equation, absolute pressure equals gamma H. The atmospheric pressure at standard condition is 14.7 psi or pounds per square inch equals to 62.4 pound per cubic feet times height. Now, take note that this is a gamma. This is a specific weight, not a density. Why? Sometimes it is sometimes specific density, specific weight and density are equal because of the neglection of mass. When we assume mass is equal to 1, therefore the density and the specific weight is equal. So therefore, its gamma is 62.4 pound per cubic feet times height. Therefore, we can simply solve its height, which is 33.92, feet. Take note, we use conversion factor of 144. Since it is in pounds per square inch, we should change the square inch into square foot, which is 12 squared. 12 squared is 144. So cancel feet squared, cancel feet squared. All we have left is feet. So cancel pounds here. All we have left is feet. So therefore, the answer for the height is 33.92, 3076.92 feet. Okay, let's go to problem number 2. Problem number 2, the pressure of a boiler is 9.5 kilogram per cm squared. The barometric pressure of the atmosphere is 768 mm of Hg. Find the absolute pressure in the boiler. Now, it is very easy for us to solve the absolute pressure since there is a given barometric pressure and atmospheric gauge pressure rather. Sorry. But here is the catch. The unit of the gauge pressure is not the same as the unit in atmospheric pressure. So therefore, we have to centralize all the unit first. We have to make this atmospheric pressure into a kilogram per cm squared. So our mother equation, our general equation is absolute pressure equals atmospheric pressure plus gauge pressure. Whereas our atmospheric pressure is equal to gamma H, which is equivalent to specific gravity gamma H, which means since it is at standard condition, we assumed already that the density is 100 kilogram per cubic meter. Now, why, if the problem did not stated its condition, we assume that it is a standard condition. So therefore, when you found a barometric pressure that is mm of Hg, we have to convert first the mm of Hg into mm of water, or we simply change its dense fluid into water. So therefore, mm of water should be converted into mm of, mm of Hg should be converted into mm of water. So therefore, 13.6, what is 13.6? 13.6 is the specific gravity of Mercury. So don't forget to memorize or to know the specific gravity of Mercury, because it is also a common constant for us engineers in a standard condition. 13.6 times its gamma, 1,000 kilogram per meter cube. Now again, this is not a density, but it is a gamma since we don't have mass. And 0.768 meter. Where did we get it? By simply converting 768 mm into meter. That's why 0.768 meter over 10,000 squared cm squared over meter squared. Where did we get the 10,000? 10,000 is the conversion of a cm squared to meter squared and vice versa. Therefore, 100 cm is equal to 1 meter. So 100 squared cm squared equals 1 meter squared. Therefore, 100 squared is equal to 10,000. And the absolute pressure is 1.04448 kilogram per cm squared. Now, since our absolute pressure is in kilogram per cm squared and our gauge pressure is at kilogram per cm squared, we can now simply substitute all the values given to this general equation, which is absolute equals atmospheric plus gauge equals 1.04448 kilogram per cm squared plus 9.5 kilogram per cm squared. That will yield to 10.54448 kilogram per cm squared. And that is the final answer. Next, for the absolute pressure, just like what I said earlier, that absolute pressure is equals to gamma H, where H is the height of column of liquid supported by absolute pressure. If the liquid used in the barometer is mercury, the atmospheric pressure becomes just like what I used on the latter portion of the problem. It's the specific gravity of Mercury is 13.6, and it's the gamma, 62.4 pound per cubic feet, and its height in inches. Now, where did we get 1728 inches cube over feet cube? Now, it is a conversion also. 12 inches is equal to 1 foot. Therefore, 12 inch cube is equal to 1 feet cube, 1 foot cube. So 12 cube is equal to 1728. Therefore, its absolute pressure is 0.491 times its height, pound, which is in pounds per inches squared or PSI. And also where H equals column of mercury in inches, PG equals 0.491 Hg, and P 0.491 H. This is the conversion, or this is the formula in getting atmosphere and getting absolute pressure. Now, for better understanding of the concept, here is problem number 1. Problem number 1, a pressure gauge registered 40 psig in a region where the barometer is 14.5 psia. Find the absolute pressure in psia and in kilopascal. By the way, kilopascal is equivalent to kilonewton per meter squared. Since Newton is force and meter squared is a area. Force over area is equal to pressure. Now, here we have a pressure gauge which is 40 psig and the barometer which is 14.5 psia, which means it indicates a atmospheric pressure. Now, we can simply use the general equation at absolute equals atmospheric plus gauge pressure. Why? 14.5 psia and 40 psig is equal in unit. The only difference is it's G and it is A. Why? When we say PSIG, it is a PSI gauge. When we say PSIA, it is PSI atmospheric. So we denote each unit by its equivalent pressure. So therefore, 14.5 psi atmospheric plus 40 psi gauge is equal to 54.5 psi absolute. So we already come up with the answer. Letter A is 54.5 psia. Now, we have to convert 54.5 psia into kilopascal. So we first know the long method. The long method is this. We first have a conversion factor. We do a conversion. We do a derivation, which comes from force equals ma. So therefore, 1 kilogram mass is equal to 1 kilogram mass times the conversion factor to become pound mass, 2.205 over 32.2 pound mass per slug, which is 1 kilogram is equal to 0.06847826087 slug. Now, we have the mass. Next is the acceleration. We assume only that it is a one mass and one acceleration. So therefore, 1 meter per second squared, we can change it into feet per second squared by using a conversion factor of 3.28 feet is per meter. So therefore, 3.28 feet per second squared. Now substituting the value we get from F equals 2 F equals MA over proportionality constant K. Therefore, we yield 0.22460866957 pound force. See to it that the pound force is a value, no, is a unit of force. Now, after we get the force in English system, we have to relate it in Newton for us to convert English system to metric system. So therefore, it's 1 Newton. We assume also that it is in 1. 1 Newton is equal to 0.22460866957 pound force. A pound force is a measure of is a unit of force. Newton also is a unit of force. So we have nothing against with that. So therefore, we can relate. So to be able to get a 1 pound force, we divide 1 over 0.22460866957 and we yield 4.452157.379 Newton. Next, in 1 pound, we convert the we derive here 1 pound is times 4.452157379 Newton per pound times 39.37 inch per meter over inch squared. And then the conversion would be 1 pound per inch squared or 1 psi is equivalent to 6895 Newton per meter squared or Pascal. So therefore, we first get the absolute pressure at English system, which is PSIA. So we have to convert it by multiplying it to 6895 Pascal for us to yield 375,777.5 Pascal or 375.777 kilo Pascal. And that is the answer in problem number 2. Okay, next problem. Given the barometric pressure of 14.7 psa atmospheric or 29.92 inch Hg absolute, make these conversions. Letter A, 80 psig to psia and 2 atmosphere. Now, we have the general equation. Absolute equals atmospheric plus gauge equals 14.7, which is the atmospheric pressure, plus 80, which is 80 psig, that yields to 94.7 PSIA. So therefore, PSIA, PSIA, we got the answer of PSIA, which is 94.7 PSIA. Next, to atmosphere. The PSIA we get, we have to convert it into, no, the PSIG, rather, we have to convert it into ATM, which is 14.7 PSIA is equal to 1 ATM. So therefore, we only divide 80 by 14.7 and we yield 5.44 ATM. Next, letter B, 20-inch HG vacuum, 2-inch HG absolute, and 2 PSIA. Now, since we have given 9.92-inch HG absolute, we yield, sorry, we use the formula of 0.491 H, and then since where did we get 9.92 inch Hg? By merely subtracting 20 minus 29.92 yields. Since it is a vacuum, we neglect, we don't need to neglect. We said that it is a negative 9.92 since it is a vacuum. So therefore, to convert it into inch Hg absolute by using the formula 0.491 times height, we yield to 4.87 PSIA. Another example is like letter C. A letter B and letter C is very alike. No, I'm so sorry. This is not letter D. No. Okay. Letter C is 10 PSIA, 2 PSI vacuum, and 2 PA. Now, where did we get 4.7? By merely subtracting 10 PSIA to 14.7 PSIA. So we get 4.7 vacuum. To convert PSI to Pascal, we should remember 6895 constant. 6895 Pascal is equal to 1 PSI or pound per square inch. Therefore, your pressure gauge is 32,407 Pascal. Next, letter D. Letter D, 15 inches HG gauge to PSI, to torrs, and 2 Pascal. Now, H 29.92 plus 15 equals 44.92 inch HG absolute, where we should use also the formula 0.491H. It is very useful. The 0.491H formula here in this problem times 44.92, we yield to 22.06 PSIA. Then the pressure gauge, which is 15 times 760, which is the conversion factor of torr, and then over 29.92 equals 381 torr. 760 mmHg is equals to 760 torr. Don't forget that conversion. Next, the pressure gauge, which is 0.041 Hg also, which yields to 0.491 PSI per inch times 15 inch times 6895 Pascal per PSI, which is the conversion also to Pascal. Therefore, we yield 50,780 Pascal gauge. And that is for the number 2 problem in pressure. So, we already finished discussing all problems pertaining to pressure. Therefore, we go now to temperature. Temperature, we can discuss temperature by solving this problem exercise number 1. Number 1, derive the relation between degrees Fahrenheit and degrees centigrade. Now, here, we should derive the formula of each conversion of temperature. Let's say, for example, the boiling point in degree Fahrenheit is 2.12, whereas in degree Celsius, 100. the melting point, or let's say the zero is 32 degree Fahrenheit and 0 degree Celsius. Now we denote T as the missing variable. So that is on the middle of the range. So by using interpolation, or by using cross multiplication, or what do you call this? Interpolation of values, the temperature of F, this one, minus 32 over the upper minus the lower. Also, here, the middle temperature at degree Celsius minus 0 over the higher minus the lower. And by two equation to unknown, we yield into this kind of equation, which is in temperature in Fahrenheit conversion. If you want to convert Fahrenheit with given Celsius, you have to multiply it by 9 over 5 degrees Celsius plus 32. If you want to convert Fahrenheit to Celsius, you have to use this one, 5 over 9 times its temperature in Fahrenheit minus 32 to be able to obtain a degree centigrade or degree Celsius. Now, take note of these three. Absolute temperature is the temperature measured from absolute zero. And absolute temperature is the temperature at which all molecular motion ceases. And lastly, absolute temperature will be denoted by T. Thus, this is the derived formula in getting an absolute temperature. The absolute temperature in metric system is Kelvin, sorry, and the absolute temperature in English system is Rankine. So therefore, temperature Rankine is equal to temperature in Fahrenheit plus 460 degree. Sorry, this is a degree Rankine in unit, and then in the temperature in Kelvin, we have the Celsius plus 273, which yields to a Kelvin Kelvin unit. Okay, and that's all for the part 3 of the module. And ano, we go. Okay, this is not okay. Temperature is not the last one, but this one, conversion of mass. Conversion of mass, the law of conversion of mass states that mass is indestructible. Yes, it is very correct that the law of conservation of mass states that the mass is indestructible. When we say conservation of mass, we have to conserve mass. So therefore, if we're going to use the mass, we should extract also its mass. Therefore, if the mass leaving is equal to mass entering, or vice versa, the mass entering is equal to mass leaving. That is the concept of conservation of mass. Let's say, for example, volume flow rate is equal to area times its velocity. Also, applying the law of conversion of mass into a mass, we yield this one. The area 1, velocity 1 over volume 1 equals area 2, velocity 2 over volume 2. So therefore, the concept of mass entering equals mass leaving is like this. We equate the entering equals the leaving. For better clarification of the concept, here is problem exercise number 1. Now, two gaseous streams enter a combining tube and live as a single mixture. This data applies at the entrance section. Now, this is the condition. For one gas, A1, its area is 75 inches squared, its velocity or speed is 500 feet per second, and its volume, flow rate is 10 cubic feet per cup. Sorry. Next condition for the other gas, which is the tube 2. Area 2 is equal to 50 inches squared. Its mass is 16.67 pounds per second, and its density is 0.12 0.12 pound per cubic feet. Now, at the exit, this is the condition. Velocity is equal to 350 feet per second, and its volume, current is 700 cubic feet per pound. Now, what are we going to find? Letter A is the speed at section 2. This one. Just like what I said, conversion of mass, any mass entering is equal to mass leaving. So therefore, if there is two streams and the problem says that it is lived in mixed, therefore M1 plus M2 is equal to M3. Okay? Any parameters like A1 plus A2 equals A3. Density 1 times plus density 2 equals density 3. Okay, now let's go back to A, the speed. The formula for speed is mass 2 over area 2 density 2. We have mass 2. Mass 2 is 16.67 pound. The area 2, which is given also 50-inch squared. Then your density 2 given also 0.12 pound per cubic feet. So therefore, we can compute its velocity. Now, take note of the unit analyzation. We have to cancel out unnecessary units for us to obtain a correct value and correct unit, a correct value and a correct unit. So therefore, letter A is 400 feet per second. Now letter B, the flow and area at the exit section. When we say the exit, when we talk about exit section, this is it. This M3, this the area of this M3, this section. So therefore, using the equation, just like what I said earlier, mass 3 is equal to mass 1 plus mass 2. Therefore, we have a mass 1. We have mass 1, which is, okay, sorry, we don't have mass 1. So we will obtain mass 1 is equal to, okay, sorry, this is mass 1. Sorry for my typographical error. Okay, mass 1 is equal to area 1 V1, sorry, area 1 V1, area 1. Area 1 V1, area 1 velocity 1 over V1, which is 75 over 144 conversion times 500 feet per second, which is the velocity over its volume flow rate, which is 10 feet per, ito yon, pound, 10 cubic feet per pound. Therefore, we have a mass which is 26.04 pound per second. Now, we have also mass 2. Mass 2 is 16.67 pound per second. So therefore, mass 1 plus mass 2 is equal to mass 3. So for us to obtain an area, the parameters is mass 3, volume 3, and the speed 3. We have given a speed 3, which is 350. Sorry, this is a speed 3. Yeah. The mass 3, which is 42.71, and the volume, which is 7 cubic feet per pound, over its velocity, which is 350 feet per second. So, summing it up, evaluating, simplifying it up, we yield to 0.8542 feet squared. So, therefore, this is the area at the exit section. So, that's it for the module 3 of, that is for the part 3 of the module 1, which is the basic principles, concepts, and definitions in thermodynamics. Our module 2 will be a conservation of energy, but this is for the next episode of our video. So summing it up, we have different parts of Module 1, which is Part 1, which is the systems of units, the Part 2, which is the specific gravity, specific weight, density, then the Part 3, which is the pressure, the temperature, and the conversion of mass. That's it for my Module 1. Thank you.